In this example, we're going to solve for the length of the shorter side of each of the following triangles as an algebraic expression of x. This example is going to lead directly into the next lesson involving the main three trigonometric functions, because in each of these cases, we have triangles defined with particular angle measures, but with arbitrary sides that are just particular ratios of each other involving algebraic expressions of x. With this concept, we're going to be able to apply similar triangles to any situations where we have triangles with this particular angle measure setup. If I have any triangle with an angle measure of 30, a 60, and a 90 degree, then I should be able to relate the side lengths because they will have the same type of ratios. In this case, I'm just going to first deal with the one where we have a 30 degree measure, a 60 degree measure, a 90 degree measure obviously, as well as the side length of x labeled across from the right angle measure. That means we have x labeled as our hypotenuse. Unfortunately, I don't have any other labels for either of the other two side lengths. If I did, I would just use the Pythagorean theorem to come up with an algebraic expression. We have to be a little bit more creative here in order to get to that point though. In order to work with this triangle a little bit better, what I'm going to do is I'm going to reflect and make a mirror image across the horizontal line that the bottom leg of this triangle sits on. So, if I draw that, that would look something like this, with a 30 degree measure here, a 60 degree measure here, and this side would be labeled again as x. If you look at the overall triangle though, on the outside of this triangle here, this is a triangle with three angle measures, 60, 60, and 60. This is a special type of triangle known as an equilateral triangle. An equilateral triangle has three equal angle measures, but also three equal side lengths, meaning that this top side length is x, this bottom side length is x, and also this side length here is also x. What that then implies about the original triangle we are working with is that this vertical side length here at the top is half of that side length x. So I can label that as x over 2 or 1/2 times x. For the future, I'm going to use the latter version of this. So I'm going to use 1/2 times x. Therefore then, I have this same right triangle with hypotenuse side of x, vertical side length of 1/2 x, and I should now be able to use the Pythagorean theorem to solve for the third side. I'll call this third side a for the time being. Using the Pythagorean theorem, a squared plus b squared equals c squared, where a squared is the side length I'm trying to solve. B squared would be 1/2 times x quantity squared, and c squared would be x squared. That will give me a squared plus 1/4 times x squared equals x squared. And again, trying to solve for a here, I can move the second term over to the right by subtracting it, which will give me a squared is equal to 1x squared minus 1/4 x squared is 3/4 or 3/4 x squared. If you take a square root of both sides here, a squared will just become a. And for the right side, I can do the square root of 3, just leave it as it is. The square root of 4 is 2, and the square root of x squared is x. So I now have my third side length as square root of 3 over 2 times x. Now let's look at that second example. This example is going to take a little bit less time than the previous one. This is because we don't need to do any special tricks with reflecting this triangle over another horizontal in order to figure it out. If you look at what we are provided for this right triangle, we have two angle measures that are both 45 degrees. This already is another special type of a triangle. It is not an equilateral triangle because we have three different angle measures. However, it is an isosceles triangle. An isosceles triangle is one defined with two angle measures that are equivalent. When you have an isosceles triangle with two angle measures, that also means that the sides across from those angle measures are also equal to each other. So, with that in mind, if you call one of them A and one of them B, then really A equals B in this case. Those two side lengths are equivalent. Therefore, if I go directly to applying the Pythagorean theorem here, a squared plus b squared equals c squared, well, c is our hypotenuse, x, so that's x squared, and the two side lengths a and b, we can call them equal to each other. So, for example, I could replace b with a and have this as a squared plus a squared equals x squared. Just like the previous question, all I need to do is solve for a. A squared and a squared will make 2a squared. In order to solve for a, I need to now remove that 2 as well as the exponent. I will first divide 2 from both sides. I will get a squared is equal to, I will rewrite the right side as 1/2 x squared. And then I can take the square root of both sides to get a by itself. The square root of a squared is simply a. The square root of 1 is just 1. The square root of 2 cannot simplify any further, it's just square root of 2. And then x squared, the square root of that is just x. Now I can leave it like this. However, if you've gone through some algebra classes, this may strike a nerve here because we have a square root or radical in the denominator. We typically do not like to have radicals in the denominator, so what I'm going to do is rationalize this fraction of 1 divided by root 2. In order to do that, I'm going to take 1 divided by root 2, and I'm going to multiply the top and the bottom of that fraction by the square root of 2. Overall, that means that I'm not changing the value of it because I'm multiplying by a number that is one number divided by itself. So I'm essentially multiplying by 1. However, if you do multiply this through, 1 times the square root of 2 in the numerator is simply the square root of 2. And in the denominator, square root of 2 times square root of 2 is 2. So I will rewrite this as a is equal to the square root of 2 divided by 2 times x. This also should look very similar to the previous solution where we had the square root of 3 divided by 2 times x.